Hello all. So in last set of videos you saw what is current density, and what is continuity equation for a current density and current, and you also saw the conductors. What is conductor? What is the property of the conductor? In conductors we also saw the Ohm's law in point form. Then we came to dielectrics. So in dielectrics you studied what is polarization and the dielectric strength of a dielectric material. So next we will see the boundary condition. What do you mean by boundary is, so when the field or flux density travels from one medium to other medium, so the interface between the one medium to other medium, the boundary between from one medium to other medium, so how this field will change, or how this flux density will change when it travels from one medium to other medium. So normally the field and flux density is calculated by using the equation for work done and the Gauss law. Using these two equations, that is the surface integral of E dot dl and the Gauss law equation, we will use, and we will find what is the flux density and field intensity at the boundary. Normally we will occur two cases. One is, so when the boundary between the two materials, that is one material is a conductor, other material is a dielectric. One material is a conductor and other material is a dielectric. This is the one case. Other case is a one material is a one type of the dielectric material, and other case is a other material is a other type of the dielectric material. Say if the first material has the permittivity of epsilon 1 and second material has a permittivity of epsilon 2. In that case, so what is the field, what is the change in the field when it travels from one medium to other medium, and what is the change in the flux density when it travels from one medium to other medium. As you know, so we will split the field and flux density into two components. One is normal vertical component, other one is horizontal component. The vertical component is taken as normal component and horizontal component is taken as tangential component. So in each boundary cases, we will find what is the tangential component of flux density and field intensity. Also we will find what is the normal component of flux density and field intensity. So we will observe these two cases. One is the boundary between the conductor and free space. Other case is boundary between two dielectric mediums. First we will take up the first case, that is boundary condition between the conductors and free space. So consider a boundary as shown in this figure. It is between conductor and free space. So you know the free space is a dielectric medium where epsilon, that is permittivity, is equal to absolute permittivity, because relative permittivity of this medium is the relative permittivity in the free space is equal to 1. So epsilon is equal to epsilon naught in free space. Now when the field travels from this conductor to free space, what is the field and flux density at the boundary of the between conductor and free space, we have to study here. So first you have to find what is the electric field intensity at the boundary and what is the electric flux density at the boundary. So we have to observe these two. So to find this one, what is the field and electric field intensity at this one, we know the property of the conductor. We already studied the property of the conductor. The first property of the conductor is, so there is no charge within the conductor. There won't be any charge within the conductor. So the rho v, that is volume charge density in the conductor, is equal to 0. But we know that the charge can accumulate in the surface of the conductor. Charge can accumulate in the surface of the conductor. So there will be a surface charge density in the conductor. If the charge is 0, then what is the field inside the conductor? Field intensity also 0. So inside the conductor, field intensity also 0. And if the field intensity is 0, then flux density also 0. If the field intensity is 0, then flux density also 0. So E and D, that is flux density and electric field intensity inside the conductor, is equal to 0. Now I will split this flux density and field intensity in two components. So one is the one is the normal component, other one is the tangential component. So I will consider E in this direction. So the electric field, to first I will find what is E, that is tangential component of E, then I will consider the flux density normal component. So first I will consider the electric field intensity in this direction. Now to take the, I will split this the flux field intensity into two parts. One is the normal component of field intensity, other one is tangential component of the field intensity. So tangential means it is a tangent to this curve, so it is touching only at the point, then it will be parallel. So I will split this into normal component and tangential component. It will be like this. So if I split into tangential and normal component, it will be like this. So this will be tangent to this curve, and this is normal to this surface at this point. It is normal to this surface at this point. So this is a normal component and tangential component. Now to find this normal component and tangential component of this electric field intensity, I will use a closed path. I will use a closed rectangular path as shown in this figure. So ABCDA is the closed rectangular path with the width of delta W and height of delta H. So width of the delta W and height of delta H, and the direction of the electric field intensity in this closed path is from A to B, then B to C, then C to D, and then D to A. This is the direction A, B, C, D, A. In the clockwise direction, the field will move. Now, if you observe this diagram, half part of the rectangular path is inside the conductor and half part is in the free space. So half part, that is delta H by 2 part, is in conductor and delta H by 2 is in free space. The direction of the field will, as I told, A, B, C, D, A. That is A to B, then B to C, then C to D, and then D to A. This is the direction of the field I am considering here. Now, to find what is work done to move a charge from A to again point A using in this path. So as you know, work done in a closed path is equal to 0. Work done in a closed path is equal to 0. So we can write the closed integral of E dot dl, which is equal to 0. The closed integral of E dot dl is equal to 0. So what is this E dot dl? It is the closed integral of E dot dl means what is the work done to move this unit charge from A to B, then what is the work done to move this unit charge from B to C, then again what is the work done to move this unit charge from C to D. Similarly, what is the work done to move from charge from D to A. So it is a sum of work done at this path, work done at this path, and work done at this path. So work done at this path. So we can split this integral into 4 parts. One is from A to B, then B to C, C to D, and D to A. So we can write this integral as the integration A to B E dot dl, integration C to B to C E dot dl, plus integration C to D E dot dl, plus integration D to A E dot dl, which is equal to 0. I will take this as equation 1. Now if you observe this path C to D, it is in the conductor. So C to D is in the conductor. So inside the conductor, as the property of the conductor, inside the conductor charge is 0. If the charge is 0, then field inside the conductor also 0. So the field corresponding to C to D is 0. So we can say integral from C to D, that is this third part of this equation, that is C to D E dot dl, will become 0. So then this equation will become the C to D is 0, then equation 1 will become only 3 terms, that is A to B, B to C, and D to A. Now we will find all each term, that is A to B, B to C, and D to A individually. Then we will add, then we will obtain what is the component corresponding to this equation. So first I will take the path A to B. I will take path A to B. If you observe here, the path A to B is parallel to tangential component. The path A to B is parallel to tangential component, and it's in the direction of this path, field and electric intensity is in the same direction. I can take field in this path is equal to E tan. So field in this path is equal to E tan. And what is the length of this path? And delta W. So this path length is constant, and I can take field intensity at this as constant, so which is equal to E tan, and I can write this integral A to B as A to B E dot dl, which is equal to, I can take E is a constant, so outside, so A to B dl. What is the length of dl? So it is delta W. So E into delta W, which is equal to E tan delta W. I will take this as equation 3. So we got first term, that is A to B. Now we will find what is the term corresponding to B to C and D to A. So if you observe these both the paths, that is B to C and D to A, half part of the path is in the conductor and half part of the path is in the free space. If you consider path B to C, the path from B to 1 is in free space and 1 to C in the conductor. So field inside the conductor is 0, but the path is split into two parts. One is free space and one is at. So delta H by 2 part is in free space and delta H by 2 part is in conductor. So this equation can be written as, so this A to D, that is D to A path, can be split into two parts. One is from A to 2, other one is 2 to D. So I will split into D to 2 and 2 to A. So we can split like this. So but if you observe here, D to 2 is inside the conductor. D to 2 is inside the conductor and 2 to A is in free space. So inside the conductor field is 0. So this integral term becomes 0 and this integral term will remain. So we can write, so taking E as a constant, here E is 0. What is E here? It is parallel to normal component. E is equal to En. So I can write this equation as 0 into what is the length of this part, D to 2 is delta H by 2 and 2 to A also delta H by 2, and field intensity at D to 2 is 0 and field intensity at 2 to A is En, because it is parallel to En. So I can take, so integration will become En into delta H by 2. I will take this as equation 4. So next we will find what is a field corresponding to path B to C. So here, if you consider here, direction of the B to C is moving from B to C. So direction of the field is moving from B to C, which is opposite to this En, this normal component, which is opposite to normal component. So it is negative of normal component. Similarly here also we can split into two parts, half part in free space and half part in conductor. So in conductor electric field is 0. So I can write this equation also in two parts, B to 1 and 1 to C. In the part B to 1 it is a minus En, and because it is opposite direction of the normal component, and so I can write this equation as minus En into delta H by 2 plus 0 into delta H by 2. 0 is because this 1 to C is in the conductor, so field in the conductor is 0, and B to C is minus En because it moves from the B to C, it is opposite to the direction of En, so it is minus En. Now we can write the equation 5 as B to C as En minus En into delta H by 2. Now substituting equation 5, 4, 3 and in 2 we will get, so E tan delta W plus En into delta H by 2 minus En into delta H by 2, which is equal to 0. So simplifying this, we will get E tan into delta W equal to 0, but delta W can't be 0, it is a particular constant value, finite value. So we can write the tangential component of a field is equal to 0. So we can write, so this is the tangential component of field. Similarly, tangential component of D can be written by using a relation between D and E. You can write D tan is equal to epsilon naught into E tan, which is equal to 0. So these are the tangential component of field and flux density at the boundary. So And next we will see